Hello friends, me again, Dr. Patterson. In this video, I'm going to talk about stepper motors and the XY tables that we would use in the lab, but I made an emulator slash simulator of in MATLAB, and also some more around what I've used stepper motors for. So hopefully by now you've watched that kind of that intro video on stepper motors, which has much better animations than I am capable of. And then we're going to look at some slides. I've got them in OneNote just so I can write some notes and draw some stuff on top of them. But most of the inexpensive CNC or computer numerical control devices that you've seen, I can group most of you into a much younger age group than I am. But it's as you've grown up, there have been more and more of these machines, starting with 3D printers, kind of around the 2005 and onward time frame. Incredibly cheap now. 3D printers are available, some on the order of like $150. Not ones that I'd recommend buying, but they are there, and they all use open loop stepper motors for, or at least open loop control of stepper motors for moving things around and extruding plastic. The drivers and the motors are incredibly cheap options. There's a huge range of different types of stepper motor drivers now. I think this picture is one, specific one, Allegro. Oh, now I got to look at the number. Yeah, it's 49.88. It's you can get, I think, 5 to 10 of these for on the order of like 10 to 15 bucks. They're incredibly cheap ways to have a relatively high precision, kind of incremental movement. And so that's what stepper motors are great for, is they take those tiny steps moving. The cheap ones, the one I've got in the video here, and also some of the other ones are usually 1.8 degrees per step, or that's the most common type for this particular size of motor. There's also a 0.9 degree step motor. Usually those are a little more expensive. You get higher level of precision, the different motor characteristics, different amounts of torque out of either one of those. You can also go much larger steps. There are ones that can do 7.5, 15, or not 15, 7.5, I believe 30 degrees as well for some of them. You can get larger and larger steps, and you get different characteristics for those motors, but it's that same idea of I provide a specific signal and it steps from one location to another. And one of the reasons that I really like these motors and use them in a lot of projects, they don't have great speed, they don't have great torque, but what they do have is like crazy precision for a very small amount of money. And so if you hook these up to a belt system or a lead screw or a ball screw system, again, you don't have to spend a ton of money to get a very high level of precision and not require any type of feedback. We'll talk more about that in a second. And this has allowed me to create a bunch of devices in the past. These are some of the 3D printer kits that I have designed and then put together for a 3D printing class that I teach at MSOE. The one on the left is, I believe, the first iteration. Then I made some improvements assembly-wise. I got it down from students assembling it in 3 weeks worth of classes down to this second iteration was they did it in 2 weeks worth of classes. I'd like to get it to 1 week, but there are so many inexpensive 3D printer options now. I'm not sure that it makes sense to keep doing my own kit through the bookstore. But what I've done with that is also there's a 3D printer cart that is in SG01 where the large red wind tunnel is in the science building. And those are all hooked up to an email system that I came up with where you can email, send from your MSOE address, send an email to it with a 3D model attached. It processes the file and everything and then starts printing it. And these are all of the axes on these are, for each one of these, There's 3 stepper motors for X, Y, and Z motion, and then a 4th stepper motor, which it drives all of the plastic filament through the machine. So if I were to actually draw, like I said I was going to, so this is the Y motion. This back and forth here is the X, up and down is the Z, and then the filament going through here is typically referred to as the E, or extruder axis. And you can have different CNC machines that have beyond XYZ additional axes as well. It's usually A, B, C, and then from there, I believe it goes to U, V, and W. I would need to double check on that. I've also built a relatively large format CNC router. So again, this is stepper motor, slightly larger stepper motors for the X-axis, the Y-axis, and then the Z-axis. And this is essentially just taking that 3-axis setup, putting a different frame to it to be able to withstand significantly larger forces than the 3D printer, and putting a router on it instead of a 3D printer printhead, and then driving it around and cutting away material. On this one, I could actually just replace the router with a 3D printer printhead, and it would be able to run the exact same code as the printer and print onto whatever I put under it. I probably would not do that because this particular setup out in my garage where there are extreme temperature variations would not be the greatest setup for a 3D printer. On the right here, I have another setup where I've got, instead of a 3D printer printhead or a router, I've got a laser attached to it. It's a small diode laser. I've got a CO2 laser one in my office at MSOE, but this is the Y-axis. Back and forth here is the X-axis. There's no Z-axis on this because it's a low-power laser diode. I think it's, oh boy, I think it's 2 watts. Not important. But what it does is it just turns it on and off. So the laser turns on, it shoots down. You can see somewhere around here, there's some like Olaf looking characters for stuff that I've laser cut for my children. So it's just another CNC device where it uses stepper motors to move, control the motion along multiple axes to move from one position to another and do so incredibly accurately. For this particular setup, I actually used this one and tested out this laser diode. I tested out to try to see how accurate I could etch circuit boards. And so the choice was either a CNC mill where I'd actually cut away some of the copper on the circuit board, or essentially etch away the material using a set of chemicals. And the end mill that I was using had essentially a better setup than the laser setup I was using. So it won out in the short term, but I still keep the laser around because it is fun to make small things like custom laser engraved cards or different materials for people. One of the applications that I found the most entertaining to make was actually using stepper motors in multiple axes to drive pumps. In this case, instead of taking incremental rotational motion and turning it into a linear motion, which we'll talk about in a minute, I had it run a pump. And so it was literally like, how much liquid could I pump with this stepper motor per step? And so I did a bunch of testing and I came up with, well, when I rotate it, let's say, I think it was for like 30 seconds, I forget how many times around it did, I got so many ounces of fluid out of it. And so I was able to calculate per step of the stepper motor exactly how many ounces were dispensed. And so I made a bar bot, or an automated bartender, that used a bunch of these stepper motor driven pumps and would essentially pump all of the, well, the ingredients for each of 5 different drinks, mojito, margarita, I made it and I don't remember, mojito, margarita, Long Island, brandy old fashioned, and whiskey sour. Those were the, I don't drink. Those are the drinks other people chose. So those are the 5 that I had it dispensed from, I believe, 17 different bottles into a cup, depending on which button you pressed. And so it's literally just taking that incremental motion, which I know is very accurate, and getting a very accurately dispensed drink. I didn't try any of the mixes ahead of time. That probably would have been more wise than trying to accurately dispense different amounts of alcohol for drinks that may or may not have tasted that great. So one of the fanciest applications that I've implemented stepper motors in was the 3D printer setup that actually started a 3D printer company back in 2011, ran for 5 years, and we ended up making a 4-color 3D printer that was also a 3D scanner. So it had all of these kind of, it's hard, you can draw. Each one of these 8 setups down here is one of those stepper motor drivers. And these were where all of the stepper motors were plugged into. You can kind of see over here, I've got 4 colored wires going into one of these stepper motor drivers. And that was the control board for our 3D printer, which, like I said, there were 4 extruder axes up here. There were 2 motors that drove the Z axis. We didn't have our typical Cartesian setup. We actually had a rotational platform. This was, what did we call it? I believe theta. And this was our, I'd have to assume R. I need to go back and check. I'm embarrassed. I don't remember. So we had R, theta, and Z axes with 2 on the Z, so 4 motors there, and then 4 extruder drives, all using gears to push plastic through. So we're controlling 8 stepper motors and doing so very accurately, so that we could print out objects that, like for this one, if I erase that, you can actually see. This was a picture of it. I had made a little Lego figure sitting on a horse and then 3D scanned it into our 3D modeling software, which we made too. So it was kind of an entertaining application of it. We're aiming for K through 8 classrooms, so this was like perfect target market, Legos and Minecraft type software and 3D printing all in one. So the big thing about why, or one of the main things about why controlling these accurately is very inexpensive and very easy to implement in software is that most of these devices, 3D printers, CNC routers, laser cutters or engravers, anything with these low-cost stepper motors, or most devices with the low-cost stepper motors and drivers, do not rely on any type of feedback. And so with open loop control, it's the eraser. There's something, or you're trying to control a motor. You've come up with some path, and that path really, it's a better way to put this. You've got a program, right? And that's what we're going to do in lab. We're creating a program. We want it to, our program says move motors. It does so very enthusiastically, right? Move motors. And it sends the signal either from our computer to the microcontroller, or if you program the microcontroller directly, the microcontroller, both of them are effectively sending signals to the motor driver. And the motor driver is controlling the motor. right? So that's open loop. We are just crossing our fingers and saying, let's hope nobody has like put their arm in the middle of the machine or like put their body in and put some type of obstruction to prevent these motors from operating like they're supposed to. And again, we're going to cross our fingers that we did enough testing ahead of time that the acceleration curves and the velocities that we're using will work perfectly for our machine. And so we don't need to worry about it not moving correctly, right? And the difference between this open loop approach, which is much easier to program, and you'll see this week for lab, like it is very easy to just tell a stepper motor to move until something else happens. That's a big part of why these systems can be so inexpensive and quickly put together, is that you don't have to worry about what's actually happening with the system. Now, if you wanted some way, so this would be open loop. Now, if we wanted to say, what happens if we implement a closed loop system? We're effectively doing the same thing. Let's see if I can, that didn't work at all like planned. All right, let's just draw it again. We're saying move motors somehow, right? We want to come up with a program that tells the motors to move in some pattern, draw a line or shoot a laser along a specific line or drag one of those router bits through a piece of material in a specific pattern. And so it's telling the motor driver what to do, and it's controlling the motor, right? And what's different about the open loop versus closed is that now we are actually going to watch what the motor does and say, this is kind of a device there, so we can use encoders of all different types. With CNC machines, a lot of times it's like an optical encoder, which is like you literally using like black or white or black or clear pieces of material moving or rotating past sensors. And so we can see exactly when it is or is not taking steps. There's also linear encoders, which if you put on a CNC machine will tell you how far along that axis you've moved. There's optical ones, there's magnetic ones, there's electrical ones, there's all different types of ways to tell if you're actually moving or not, right? And they're usually got some type of encoder on there, and that provides a signal back to your program, which says, you told me to move, and I did or did not do that correctly. And so if the motor doesn't move correctly, then the software can adjust and say, well, you need to do this instead, or maybe turn up the power going to that motor so that it can successfully turn, or maybe it needs to slow down one of the other motors to stay in a defined pattern, right? You've got some way to feedback and say, okay, you didn't do what I wanted you to. Now I can adjust in how I'm trying to control you so that hopefully you are going to be able to follow along that path. And so this is what most of the cheap machines do. This is the 3D printers love open loop control, right? Because if you try to work with almost any of the inexpensive 3D printers, let's say anything sub, I'm going to guess sub $3,000, you will be able to go over and physically like stop the device from moving and then let go, and it will have no idea that you just prevented it from moving. And so it will continue to try to move in the pattern that it was going to at that specific time, but it will do so in a completely different spot than it was than it was originally intended, right? Because you physically restrained it, kept it from moving. Whereas with the closed loop, this is more industrial machines, right? Industrial machines use the closed loop system because most of the time these machines are much more focused on the type or how precise and accurate you can be with the cuts that you're making and repeatable, right? And if you've got a way to track what the actual motor movement is instead of what you hope it to be, then you can be much more accurate and repeatable with your movement. So that's the difference between open and closed loop. We're going to be doing open loop because it is so much easier to implement both in terms of software and hardware. The closed loop control, you can bring in a bunch of additional theory, which hopefully by the time you guys get around to being seniors, I'll have my special mechatronics elective, which we can do closed loop motor control with. But how do you do that? How would you even take a motor and take rotary motion of the stepper motor and turn it into linear motion? So there's belt systems. This particular picture, now that I look at it right now, probably not the best example because it's a pulley going to a pulley, right? But in a lot of cases, you will have like a motor, a stepper motor, we'll say stepper, down at one end of a piece of material that is essentially the support or structure for a linear axis. You've got a carriage, and there's a pulley on here. And this has a belt that goes and connects to this, has a belt that loops around to the other side, and there's usually a pulley here, and then loops up and connects to the other side. And so as this stepper motor rotates back and forth, we can actually control the linear motion of the carriage. And so what if we wanted to calculate how many millimeters of movement per step we would have, right? And I've got the example that I chose is something called the GT2 belt. And a GT2 belt is a specific profile that has, this is essentially an engineering drawing of the profile. And the pitch is what we really care about here. For a GT2, we're actually looking at the pitch is 2 millimeters. And so it's from the center of one tooth to the center of the next. Did I grab the wrong diagram? No, the pitch is 2. What is this one talking about? Pitch length. That's something different. This is what we care about up here. So we've got a GT2 belt. We've got 2 millimeters per tooth from one center of one tooth to the center of the next. Well, all we need to know then is what is the number of teeth on the particular pulley attached to our stepper motor. And so if we were to say a common number of teeth on a pulley for a 3D printer, there's ones that are 12, 16, and 20. Let's pick 20 teeth, right? That means for 20 teeth, all the way around the pulley, I'm not going to try to, nope, not going to try to draw 20 teeth here. Oh, come on, OneNote. It's not going to let me. I'm not drawing a circle. Stop it. This is why I don't even try to draw. But it's got 20 teeth all the way around. That means when we do one full revolution, one rev is equal to 2 millimeter pitch times 20 teeth. This is 2 millimeters per tooth times 20 teeth. So we've got this is equal, the total movement we're going to get out of this is 40 millimeters per revolution. All right. And so now we spin it once, just once all the way around. We've got 40 millimeters of travel. And the stepper motors, because they're set up in a way where they're either, the most common ones are 1.8 degrees, there's also 0.9 degrees. That tells us the number of steps per revolution. And so we can say for the 1.8 degree, we would have, for 1.8 degree motor, we'll say stepper, we'd have 200 steps per revolution. And so that tells us that for this particular setup, where we've got GT2 belt, can't write today, 20 tooth pulley, and a 1.8 degree stepper, we will have, and I'll give myself a little more space, our steps per, or sorry, nope, disappointing, Dr. Patterson, millimeters per step equals our millimeters per revolution over steps per revolution, which is equal to 40 over 200. So we get, and I'm going to use my calculator because I just messed up writing so many times, 0.2 millimeters per step, right? And so we know exactly per step how far we should be traveling. So that's with a belt system. There's two other main ways to control these. Another one is using something called a lead screw, which is literally like effectively like a really long bolt, right? And you put a nut on there, like one of these, and you attach something to it, and it will drive back and forth as you continue to spin that rod. And so normally you've got a stepper motor, and I will try to draw one. And it's attached to some coupler on there, and then the motor shaft goes right in the middle, and it spins the lead screw, and we get travel back and forth. And so the example that I have this time is this is a 1/2x10 Acme threaded rod. So this one means this is the diameter, and this is the threads per inch. Right, so if we wanted to say how many millimeters are we taking per step, we'd say we've got 10 threads per inch. That means for each inch moved, or sorry, for each single thread, which means once around, one revolution, we're moving 0.1 inches per rev, which is equal to 2.54 millimeters per rev. And then we've got that, and then we can say, well, what's the motor that we're using? Let's use the 1.8 degree stepper again. We've got 200 steps per rev. So that means that we can take that 2.54, our millimeters per step, is equal to our 2.54 divided by 200. So 2.54 divided by 200, and we get, this is equal to 0.0127 millimeters per step. So again, we're just translating that rotary's incremental motion from the stepper motor, which per step can be incredibly accurate. It's usually like to each step position, it's plus or minus 5% of that 1.8 degrees, right? And so you're snapping to those positions very accurately. And then so that translated into linear movement means that this is a very small step increment, right? And if you can do that accurately, you can start doing some very like 3D printing or laser engraving or a lot of different things very accurately. And the last one, kind of like a better than, most of the time considered to be better than lead screw, definitely better than lead screws. Some people will argue back and forth about belts versus ball screws and how a lot of times these are too expensive, which they are very expensive. These are like the precision ground version of lead screws. And instead of using a threaded piece of material like that nut that we saw above, it actually uses ball bearings on the inside to follow along the precision ground curves of that ball screw. That's what it's called, ball screw, right? We are actually using these ball bearings kind of moving along the screw part so that we can get very precise movement. And there are tons of different grades of ball screws, and it usually just boils down to how precise is the movement along the ball screw over a certain length, or making sure that there's no motion like out of the axis of movement. You can buy very inexpensive ball screws, which are still probably more expensive than the belt systems. Or you can buy very expensive ball screws, which kind of go in a lot of those industrial machines, like some of the CNC lathe and milling equipment that we have in SG01. They use expensive ones, right? But that's because they're trying to obtain very accurate movements so that you can use them to make very accurate parts, or essentially very precise machining of components and features on the parts that you're creating. So if we wanted to do another example, this is, so 1605 ball screw is, this is 16 refers to the diameter. So this is a 16 millimeter diameter ball screw. So that's the diameter of the screw part. And then the 05 is the distance traveled per revolution. So we have 5 millimeters per rev. And so if we were to take that and say, well, what does that translate into? Let's do a 0.9 degree stepper this time. 0.9 degree stepper. This means that we've got 400 steps per rev. And so we can take that 5 millimeters per revolution and divide by our 400 steps per rev, and we get some days I just can't math, 0.125 millimeters per step. Can't even write today. So very small movement. there are lead screws and ball screws and uh, pulleys and belts that can have smaller pitches, larger pitches. Um, it all depends on what you're trying to achieve with the machine, and you choose one over the other for different reasons. Uh, but they all go to translating that rotary motion into linear motion. And the three things that you do on almost all these machines are: one, you need some reference point to start from. So that's moving to some type of, it's called a home position, which means you're literally going and pressing against something that tells you where to reference everything else from. So in the case of the physical hardware in lab, the switches located, so they're actually, it's kind of weird how it's wired up, but there's one switch for our x-axis that's right down there, kind of, that's the minimum position. And then the other one for the y is right there. And so the goal is to actually get this to move down to the corner. And if you have or have not watched the Arduino, this is one of my emulators / simulators that I've made. It's not in MechaGod software. This was before I started making that one. So I made the Arduino to emulate the XY table, because the biggest complaint about the XY table in mechatronics, at least, oh gosh, 5 years ago, was that they could only use the equipment in the lab. And so I said, I can help you. So I made this emulator which tells you what the state of the pins are for both X step, Y step, X direction and Y direction, and also shows you what's happening in this particular part. And so the home position is actually down here, where we'd be able to get this carriage both to go down this way and this way, and hit switches right at that, right here for the Y and right here for the X. I don't know why I'm drawing them again in that strange way. But that's the goal, is trying to get it to a specific location. So then from there, you can reference moving to, let's say if we wanted to move to an X position of 5 inches and 3 inches in the Y, right? You know exactly where to move because you have found your 0, 0. You have found your home position. And so one of the first tasks in lab is going to be recreating that function that is so important on so many CNC machines, is moving to the home position. And so we'll hopefully you'll try that first, and then if you need help, you can see the videos that I create. Find my mouse. So the next one is just a movement, and moving to a specific location, not doing so in any particular way other than just trying to get there as fast as you can. And this is usually the G0 command is one of the top 3 commands used. It just will try to move all the motors to a given position as fast as it can. So if I said, let's say I was starting at a position of 8, 8. I don't know that that's the actual position there. But if we were starting there and we wanted to move to a position of over here, let's say this is a position of 1, 7. So X equals 1 inch, Y equals 7 inches, where this is X and Y coordinates. So if we want to move there, what we would see if we said, okay, just move these motors as fast as you can, it would move from this location down. It's going to do the one node thing, downward at a diagonal, both motors moving at the same rate because they're the same motors with the same pulleys, same belts. You'd see a diagonal movement where they're moving at the same rate. And then we would get to a point where the Y coordinate after 1 inch is equal to 7 inches. And so it is done moving. And so then all it would do is move along the X axis down to 1 inch, right? And so we have a movement that does not coordinate motors together. We have two different line segments here. And so it's no coordination between motors. Each motor is just trying to get to its final position as fast as possible. The last one is a linear move. And so you're trying to coordinate movement of all the motors together so that you can move from, again, let's use that 8, 8 and 1, 7. You're going to move in a straight line. Or if we wanted to do something further down here, we would have a straight line movement to get there. And so you have to coordinate the movement of the motors to make sure that they're stepping both at the right rate or at the right times and the right number of times. And this is actually not a super trivial problem because it's not as easy as saying, well, I need to take 10 steps on this one and I need to take 20 steps on that one, and I want to move at this rate. So every, let's say 1 second, I'll step with the Y motor, and every half second, I'll step with the X motor. It's not going to work out well for you. But what there is, and hopefully you've read about this by now, that this is a problem that they had in computer graphics as well, is how do you draw a straight line on a system that does not have the ability to draw that straight line? And computer screens are not able to show straight lines, right? You can try to work with vector graphics to literally draw those straight lines, but we don't have those types of setups. We have LED or LCD screens where it is tiny little pixels turned on or off, and that's what creates the picture. And so we need a way to represent something like a straight line on this grid-based system, right? And so Bresenham's algorithm, I don't know why I have Bresenham's al on there, but Bresenham's algorithm is a technique for achieving this, drawing at least its kind of first, where it started out was computer graphics, being able to draw this straight line on a computer screen. And if you think about it, it's incredibly similar to what we have, right? Because we have stepper motors that are able to only move in increments. They do not have a continuous spectrum of movement where they can move from anywhere along an axis, right? This moving from here to here would be one step, right? Just like moving from here to here is one step. And so Bresenham's algorithm is great for stepper motor control as well, because we're literally taking these like movements along orthogonal axes, depending on the machine, most of the time orthogonal axes, to move from one location to another, and we're trying to do something like draw a straight line. And so we need, or one of the best approaches is using Bresenham's algorithm to do that. And I directed you to the Wikipedia page for Bresenham's algorithm because it's got some great pseudocode there that explains exactly what we're trying to do. And so we're gonna look at this right now and walk through how we can implement this in MATLAB. And so you've got in starting position and ending position. So this would be start and end, right? You've got x0, y0, and x1, y1. And then you calculate how much you're moving in the x-axis and then how much you're moving in the y-axis. And then based on that, you calculate what's they have referred to as a delta error, the amount of error incurred by only stepping in one axis. And then you also keep track of the total error that's accumulated as you continue to step. And so we could even, on the next line, we start at the original position, right? Y0 and X0. And this for loop, we should be able to implement almost directly in MATLAB because we can do the same thing, right? We can step from, we would say for I equals 1 to whatever, and you can specify an increment as well. And so we could specify that from x0 to x1, and the increment would be the step increment. You need to do a little more work than that. I'm not going to give it all to you now, but that's what you're doing, right? And instead of plotting here, we would actually say step in X direction. So instead of plotting on the graphics, whatever graphics display you have, we're going to say move that motor, move the X motor. And then we add that delta error onto it because we might have a diagonal line where we want to move eventually in the y-axis as well. And you keep stepping in the x direction until it gets to a point where you have accumulated enough error that it is now going to go into that if statement and say, we want to also change the y position. And so instead of this, we'll say step in y direction. And then after you've done that, you can reset the error afterwards. And so instead of plotting and changing the y coordinate to be reused in the plot, we're going to step in the x-axis and then step in the y-axis. And so exact same algorithm, we're just using stepper motors instead of graphics processors and plotting functionality. So that's the fast and dirty version of how you can implement Bresenham's algorithm in MATLAB. Give me just a second. I was going to show you this guy over here and show you just how easy it is to make these stepper motors move. All right, so the XY tables have specific pinouts, and the ones that I've used for the Arduino actually match up. And what I've done in this circuit here is I've just taken the step pin and the direction pin. So 6 goes to the step pin. Let's see if I can show this on one of these stepper motor drivers. And the pin 7 goes to the direction pin. And so I need to control those to make the motor move. So let's go over to MATLAB and we're going to start with our clear all, close all, CLC, INSTR reset, just for paranoid. And then we can make a connection to the Arduino. So Arduino object is equal to Arduino. And then we want to step the motor. And so first I'm going to define what the pins are. So I'm going to say step pin is equal to, what did I just say? I said the step pin is D6. And the direction pin is equal to D7. So now I've got the two different pins. Now if I wanted to, I'm going to tape this on there a little better. So one step is not going to be very visible. So what I'm going to do is I'm going to say for I equals 1 to 100, we will step the motor. And so how do we do that? Well, we have to supply, I believe, a rising edge. I'll pull up the documentation for it. So it's on the rising edge. That means whenever we go from 0 volts up to 5 volts, we're going to cause the motor to move one step. So we want to say in here, let's do an end. We want to go from low, a defined low, to a defined high, right? So we'll say Arduino object, I want you to write digital pin and pass it the pin. And for this, it would be, sorry if you can hear my kids in the background. We're going to tell the step pin that we want it to go to 0 volts. So we get a defined, like definite low. And then on the next line, we want it to go high to 5 volts. So we're again going to say, hey, Arduino object, write to your digital pin, and it's the step pin again, and we'll say a signal of 1. So this should go through here 100 times and step the motor. Let me turn on I have an external power supply hooked up because most of the time these motor drivers don't work with very low voltages, and it needs a significant amount of current. Usually right now it's drawing about 2/3 of an amp. I've even got the motor turned down, the driver turned down. You can have motor drivers that do multiple amps of current. For these, we keep it low just so nothing overheats, and I can have it in a breadboard instead of soldered into another situation. So we're hopefully going to see 100 steps here. So let's run this and see if I have any errors. Nope. So it moved all the way around. So this is a 1.8 degree stepper motor, and so that 100 steps got me a half turn out of it. So how could I change the direction? Well, all the pins default to low initially. So if I wanted to change the direction to the other way, I could say, hey, Arduino object, write digital pin, and I'll tell the direction pin in this case to go to a state of 5 volts. So opposite of what it was just doing. So let's try that again, and I'll hold the motor this time. And indeed, there's a, we checked, ooh, that's hot. Wow. I gotta turn that down. There's a little potentiometer on here. Wow, that's hot. So these things cannot, especially these inexpensive ones, these ones cannot handle much current without getting what I would refer to as spicy hot. Like you put your finger on there, and if you held it for 1 second longer, it would give you a burn. So make sure you don't. Well, you guys don't have these. If you do get some, which they're incredibly cheap, pretty much anywhere you order them from. One, make sure that your power supply is secured. But two, make sure you turn that little potentiometer so that you don't have too much current going through, because these chips, if you turn them up high enough, you can actually burn them out. It's not impossible to do, and I have a pile of partially burned out ones from previous student projects. So let's do that one more time, just see, hopefully, oh, let me turn on the power. So now I'm only doing half an amp. Probably already ran. Do that again. Okay, so we got our 180-degree movement. So that's moving the X motor, right? And we could do that until some button is pressed as well. So we could have this be a for loop or a while loop, right? If big hint towards the home function, you could continue to step until a button is pressed. The way that the drivers or the additional boards that work with the hardware, and also the way that I program the Arduino to emulate the hardware, they have I forget how they're set up, but we have to actually configure the pins to be pulled up so that we can have usable logic on there. So we configure the pins to be in pull-up mode, which I should totally show you right now. 1 second. All right, so what I've done is pull up the documentation page for the Arduino and MATLAB. There's this function or method on there called configure pin. And the way that the buttons are set up in the hardware that we have in the lab, and also what I've emulated in the Photoino, is that there's nothing connected to the side of the switch where you have the pin itself. We're actually implementing in the chip that's on here the ability to have an internal pull-up resistor. So we're going to configure the pin to be pulled up. So we'll use this. They list the different ones. Oh, here we go. Right down here under pin mode. So we want to use configure pin. So let's go back over here, and right after the Arduino, let's say X switch. Which one is it? I'm have it hooked up to 9. So that's switch B. Okay, so X switch B is equal to D9. And then on the next line, I want to say, hey, Arduino object, configure this pin and pass it the switch, X switch B, and then tell it what state to be set to. And if we go down, the function or the method is you pass it the pin and the mode. So the Arduino object, the pin, and the mode. You can also call it and it'll return the value if you just specify the 2 arguments, which are the Arduino and the pin number. We're not going to use that because the only time we're going to change it from the default is right now for this particular setup. And so if we go down and look at the different pin modes, the one we want is pull up. And so we're going to copy that and go over here, and our last argument here is going to be as a string. We're going to say pull up. And let's make sure that part works real quick. So all we're doing, creating the connection, we're stating what the switch pin is, and then we're configuring it to that particular one. So no errors, that's good. Let's test it now, just like we have all the other objects we've thrown in here. So let's say, hey Arduino, or while true, let's read the value from that pin. So we'll say, hey Arduino object, read digital pin, and pass it the X switch B side. And we should get back a value, either 0, it's not pressed, or 1, it is pressed, or at least that was the previous logic. And that's why I'm going over buttons again. So let's run this. Now you're going to see when it starts running, we get a value of 1, and the button's not pressed, right? And then I press it, and it's still going to be that because I don't have this wired in correctly. And I might need a different resistor. Nope. Here we go. It was in the wrong row. I press it and it goes to 0. So what I've done in the chip, there's a pull-up resistor, a very high number, or very high value in terms of ohms for the resistor, but it is essentially pulling that signal up to 5 volts. And so what it's reading most of the time is 5 volts. And that means there's nothing else connected to it. Whereas when I push this button, there's a much lower value resistor on this side. I could even put in a wire here. Let's do that. It might make more sense. We'll put the wire to ground, and when I press on that, we get that same action. We go from high to low. So it's inverted logic from the buttons we've been using so far. I am not I'm not sure why I don't think we noticed that these boards were configured this way and there's no way to change it because it's like part of the circuit that sits on top. And so that's why we've stuck with it. So it's inverted logic for the switch this time. So whenever I press it, it goes to 0 instead of 1. So when I want this motor to spin, I'm going to grab this. If we think about the while loops that we've constructed before, we'll get rid of those comments. We're going to change this loop. We're going to say while, and while the button is not being pressed, I'm going to move this over so you guys can see it. While this button is not being pressed, we want it to continue moving. So while not read digital pin switch B. The other way we could say this is while this is equal to 1, sorry. I just messed that up. No, we want to, I messed the first one up. It reads 1 when it's not pressed. And so we could have this, or while this is equal to 1. We want it to continue doing it while it's not pressed, which is actually a value of 1 in this case for this switch, which has a pull-up resistor internally on the chip that drives most of the functionality that we're using this quarter. So let's stop that. And we should see, let me turn on power supply. We should see the motor spin until I push that button. So let's run it. So we're seeing movement, and then as soon as it swings back around, I'll push it, and I pushed it, and it stopped. Right? So as soon as I pushed that button, it dropped to a value of 0 because it was the voltage that's being read by that digital pin will be 0. And so the signal coming back, or the value coming back to MATLAB, will be 0. And so this case would end up 0 is not equal to 1. So it would be false. And so it would have exited the loop and stopped, which is exactly what we saw. And so it's a different switch setup, just inverts the logic for the way that it operates. In the case of the Arduino or the XY table in class, the button is pressed when it's actually 0 and not pressed when the value is 1. This one went much longer than what I anticipated. Hopefully you watch the whole thing because this last part's important. See you later.